comes to protein biochemistry, you'd think that measuring protein concentration would be the easy part, but it turns out to be way more complicated. There are several methods to choose from. Bradford assay, UV280, BCA are some of the three main ones that you might see. And each of these has kind of strengths and limitations, and so often the one that you choose is going to be dependent on the buffer compatibility as well as kind of like the concentration you need and this sort of thing. Speed, all of these things come into consideration when you are trying to determine how to measure your protein's concentration. Knowing that the exact same protein, the exact same mixture might give you slightly different values depending on which of these quantification methods you use. And in the case of a standard curve-based quantification, it also depends on your standard curve and how good your standard curve is and how good your fit is to the standard curve and all of these various things. So it turns out to be way more complicated, but let's talk about the strengths and weaknesses of these three main methods: UV280, Bradford assay, and the BCA assay. So UV280, this is just measuring the absorption of 280 nanometer light. And if this works really well if you have a super pure protein and you know what the protein is. Different proteins are going to absorb UV280 light to different extents because that absorption is coming from the aromatic amino acids of those proteins. So our tryptophan, our tyrosine, our phenylalanine, these are going to absorb the UV280 light, but different proteins have different numbers of those amino acids, and so they're going to absorb from different extents. And you can account for this by figuring out the exact kind of amount that your protein would absorb, your specific protein based on its sequence. But that only works if you have a really pure protein, and typically you're going to have some sort of impure protein or you're going to have a mixture of proteins. In those cases, people often use like an average absorption, and that average might not be average for the proteins in your mixture. And so UV280 is great in that it's kind of quick and simple. You don't need to do a standard curve or anything, but it's limited in the fact that you can't, if you don't have a super pure protein, then you're not able to kind of accurately determine your protein concentration, and you got to go with kind of like an average, which might not be average. And if you think that your protein is pure but it's not pure, then you could kind of be biased if you're using a more specific quantification based on the protein sequence. Another limitation of UV280 is that it's not going to be that accurate at very low values, very low concentrations, and so there are methods that are more sensitive. One thing to keep in mind too with the UV280 is that imidazole, which you might be using for say your histag chromatography, your nickel affinity chromatography, imidazole is actually going to absorb UV280 light, so you want to keep an eye out for that. And if you're doing some sort of gradient, then it becomes very hard to kind of like subtract the actual background and see what the concentration of your protein is. So again, with UV280, you're measuring the absorption of light, and different proteins absorb light to different extents. You can use a tool like XPazy-Prop-Param in order to figure out how much light your specific protein would absorb, the extinction coefficient. But if you only have one protein, that works great if it's super pure, but if it's not pure, if you've got a mix of proteins, then the UV280 isn't going to be as helpful. You just got to use kind of like the average protein, which might not be average in your case. Another common type of protein quantification is through a Bradford assay. Now, a Bradford assay is a type of dye-based assay. These dye-based assays have a dye that binds to protein, any protein, and then it either changes color. In the case of a Bradford assay, you'll go from like a brown to a blue, and some of the times you have dyes that are fluorescent, they give off light, and the ones that are fluorescent have higher sensitivity, but then they require a special machine to actually measure the light that's given off, and so you need special equipment, something like a Qubit. But these can be adapted for like high throughput or like lots of sample assays, think robots and stuff. But Bradford is super duper common in the lab, and if you want to use it quantitatively, then you've got to make a standard curve to compare it to. As opposed to if you're just measuring UV280 light, there you don't need a standard curve, but for these other methods we're talking about, you do need a standard curve. And so you need to compare the blueness to the blueness of known concentrations of a protein. So typically you use something like BSA, and then you're going to make a series of dilutions of different concentrations, and then you're going to plot the concentration of the known protein versus the blueness, so the absorption of the light. So typically you do like 595 for the Bradford assay. You can do a ratio of 595 to 450 to try to get a better linear curve, as opposed to just taking 595 alone. You're going to get points that you then fit a curve to, and then you can basically take your protein, measure your protein, see how blue it is, and compare it to that standard in order to figure out what concentration your protein is. But these methods are biased too. So UV280 was biased by how many of those aromatic amino acids you had. But if you had a really pure protein and you know its sequence, you can account for that. With these other ones, however, now we are relying on comparison to other proteins which might have very different compositions from our protein. And so BSA has a different composition than, say, your protein of interest, and so this matters because the Bradford doesn't just bind non-specifically. Instead, the Bradford is biased by basic amino acids. So by your histidine, by your lysine, by your arginine, these are going to be positively charged, and the negatively charged Bradford is going to preferentially bind for those. It also can glob onto some of the aromatic amino acids. So again, you got kind of like the aromatic amino acids kind of skewing things. And so depending on how many of those your protein has versus how many of those the BSA has, or whatever your standard was, then you could kind of get more biased results. And you have to think about, okay, well, how good was my standard curve? How good was the fit to my standard curve? And so there are kind of these problems that can arise when you're trying to do quantification based on a Bradford. A Bradford also has a narrow range in which it's actually linear, and so this can cause problems. One of the nice things about Bradford is that it's really quick, except for setting up the standard curve and all your replicates and things. So what you can actually do is just do a qualitative Bradford assay if you're trying to see if they're like protein still coming off of my gravity flow chromatography column. Is there protein present in this sample versus this sample? You can kind of just mix some of your protein with some Bradford, even do it in like a microplate without even measuring the microplate, just so you have a nice little convenient receptacle, and then you can see, okay, protein is still coming off my column, protein's coming off my column here, this sort of thing, when you're not having a UV monitor with a FPLC, so some sort of like ACTA or something with protein purification machine. It's coming off a column and it's going through a UV detector, and so you're measuring the UV280 there. Not to try to quantify it, but just to kind of get like a relative amount and see when protein is coming off and what fractions it would be in. If you're doing things gravity flow, now you just got liquid flowing down through the column, and basically it's going to come out of the column, and then you can check it with a quick Bradford in order to see, okay, well, is it turning blue? Now, Bradford, one of its limitations, in addition to kind of the standard curve thing, is that it is incompatible with detergents. And so this can be a problem if your buffer, say, has some detergent in it, which is common for some applications. And so if your buffer has detergent in it, then the Bradford is not the way to go. Bradford isn't compatible with detergents, but it is compatible with most other things you might have in your buffer, things like reducing agents, something like DTT, beta-mercaptoethanol, TSEP. All these reducing agents are compatible with the Bradford, but they're not compatible with the next type of method that we'll talk about, which is the Biuret-based. These Biuret-based methods, what they do is they measure based on the protein backbone, not by kind of globbing on to the protein side chain or by measuring absorption from the protein side chain. Instead, these are dealing with the backbone, so it makes them less biased. The backbone of proteins is going to be able to basically chelate, so clamp onto copper, and it's actually going to be able to reduce the copper into a different oxidation state. And that reduced copper is then able to react with another reagent, and so it's going to react with this BCA reagent that is then going to turn purple. And so I like the BCA's purpleness, and it's nice, but I don't like that it takes longer than the Bradford. Because it's working with the backbone, then it's not biased by the side chains as much. It's compatible with detergents, which Bradford wasn't, but it's not compatible with those reducing agents. Now, they do make versions that are compatible with reducing agents, and basically you do a pre-treatment step, which from what I can tell is treating it with iodoacetamide, which is going to then kind of like cap off all of those sulfur groups in your reducing agents that would try to reduce the copper, which would then give you kind of like a false positive. And so you also can't, though, use it with things like EDTA. Anything that's going to chelate those copper ions, bind onto them, is not going to then allow you to measure protein concentration using the BCA method unless you do something like precipitate out your protein and things. The BCA method, basically your protein is going to reduce that copper, and then the BCA reagent is going to react with the reduced copper in like solution. And so it's going to increase its signal over time because the protein's still there, able to reduce more copper. And so you want to make sure that you're kind of measuring everything at the same time, and it's really important. With Lowry, here it's an endpoint based method, but it's going to be like more finicky and things than the BCA assay. Lowry's not used that much, and it's also going to be incompatible with ammonium ions, amines, and things like that. So your main options are your dye-based methods, such as Bradford and fluorescent. Those are going to be a narrower range of usefulness. There's high protein variability, and they're incompatible with detergents. With the Biuret-based methods, here, you're going to be based on the backbone instead of the side chain, so there's less variability between proteins, but it's incompatible with reducing agents without prior pretreatment, but it is compatible with those detergents. It does take a little bit of a while though, but the BCA one turns purple. And finally, the quickest, easiest is just UV280. UV280 deals with the absorption of UV280 light based on the side chains of proteins, and different proteins have different amounts of the side chains that actually absorb that light, and so different proteins absorb light to different extents. If you have a pure protein, then you can account for this if you know the sequence of the protein by figuring out the extinction coefficient using a tool like XBaseProParam. This is then going to allow you to kind of measure the concentration of your protein if you have a pure protein. If you have a mixture, then you typically use like an average, which might not be average for the proteins in your mixture. But with the UV280, you don't need to be making any sort of standard curve. You just stick it in the spec, or you stick it on your nano drop, and be careful though with the nano drop because it's not that accurate. And then you want to use that in order to figure out the concentration of your protein. With any of these methods, when you want to get really quantitative about the concentration of your protein, you're typically going to do things in replicates, and so often you do 3, because if you only do 2, then they're very different. How do you know which one's right? If you do 3, you've got more of a chance of kind of saying, okay, well, this one's probably right, and then maybe you want to go and actually do more replicates. With some of these methods too, with like the Bradford, the linear range of the Bradford is really small, and so you probably have to do dilutions of your protein in order to get to the range that is in the linear range of your standard curve. And so you might need to do that too with some of these other methods. But the BCA method has a broader range than the Bradford assay. At the end of the day, each has pros and cons, and you just want to choose one, go with it, and be consistent so that you're able to directly compare, say, one protein prep to another protein prep. And then once you know the concentration, then you can do all that fun stuff like measuring enzyme activity.